Hello, my name is Robert Smith, and I'm with New River Community College, and today we are looking at the Nernst equation again. This is the second video in a two-part series of videos on the Nernst equation. I'm giving special time for the Nernst equation because it's such a often used and useful formula. So it's used many times for many different reasons, and it's very useful for electrochemistry, which is a common technique in determining concentrations and all manner of different things. So let's get started. We can write down our Nernst equation. We're going to assume that this is it's at 298 K, so it's standard state. So we can write down Nernst as E is equal to E naught at minus 0.0257 volts over N natural log of Q. If you're not sure where that 0.0257 volts comes from, you can look it up in my previous video on the Nernst equation. So again, we're going to use the Nernst equation to solve this, and we're presented with the question of what is the concentration of protons given the EMF of the galvanic cell is 0.54 volts at standard state, and that we have a concentration of zinc ions and a pressure of hydrogen gas given. And we're given the formula that's the balanced equation, or the equation for the cell. And whenever you're given a situation where you know what the cell potential is, and you know concentrations, you should think Nernst equation. Or if you're given just concentrations and you are given a cell in general, you should think Nernst equation. Anytime concentrations and cells are involved, definitely mean in terms of chemistry, and we're talking electrical cells, you should definitely consider using the Nernst equation first and foremost. That being said, the first thing we want to do, now that we have the Nernst equation written, is split up our equations into the half reactions of the anode and the cathode. So the anode is being oxidized, and the cathode is being reduced. So 2H plus 2 electrons, H2 gas. Okay, so this is our equation that is the basis for the standard reduction potential. So a potential has an arbitrary starting point, and you can choose what your starting point is. And chemists have decided that the potential at during the formulation, when hydrogen gas, or when protons produce hydrogen gas, or and that's in the reduction form, that is zero. That is zero cell potential. And so things that are everything else in terms of the voltage is based on measuring it from that point. So our E cell is at standard state is easy to calculate. It's just minus whatever the zinc standard reduction potential is. So it would be negative that, which means that the whole thing is positive 0.76, because zinc 2 plus 2 electrons yields zinc solid has a standard reduction potential of negative 0.76, but that's the anode, so we're minus the anode. It's cathode minus anode, so you just change the sign on it. Okay, so there's that. And we can also take a look, and there's 2 moles of electrons in either half reaction, so we don't need to multiply by any factor to get them to be equal to one another. If they were different, if you had one that was 2 and one that was 3, you would want to multiply by a common factor to get the so that you have equal numbers of moles of electrons on either side, and that number would be your N. But because they're the same, we don't have to do anything other than write N is equal to 2. And then for Q is equal to products over reactants. And our products are zinc 2+, so we got 2.0 molar, times the other product, which is H2, so times the 2.0 atmospheres. But again, we in previous videos, you may have noted that I don't include the units. That's because each of these are based on standard state. So this would be like 2 atmospheres over 1 atmosphere, or 2 molar over 1 molar. So the units go away, and that's why Q is unitless. Over the reactants, and zinc we do not consider because it's a solid. So we would only consider the concentration of protons raised to the power of their coefficient. So this would be that would be Q. So this Q is 4.0 over the concentration of protons squared. Okay. And we're given that E is equal to 0.54. All right. So now what we're asked to do is find what is H plus, the concentration of H plus. So we need to reformulate the Nernst equation to accommodate that. So first we will bring our E at standard state over. So E minus E naught is equal to negative 0.0257 volts over N, natural log of Q. We can multiply both sides by -1 and get it so that it's E naught minus E is equal to 0.0257 volts over N, natural log of Q. And then we can multiply both sides by N and divide both sides by 0.0257 volts. So we'll do that next. So now we have N times E naught minus E over 0.0257 volts is equal to the natural log of Q. And then to get rid of the natural log, we just raise everything to the, everything is going to become the exponent of e to that power. So, and then we can rewrite Q in terms of 4.0 over H plus squared is equal to E to the N. I'm going to call it delta E. Delta E is equal to E naught minus E. That's what we're defining it as, over 0.0257 volts. And then we can multiply both sides by concentration of protons squared divided by E to the this whole function up here, and then take the square root. So H plus squared would be 4.0 over E to the N delta E over 0.0257 volts. So that would mean that that the concentration of protons is equal to the square root of 4.0 over E to the N delta E over 0.0257 volts. Once you get to this point, you just have to plug up. Sorry, this should not be squared because we took care of the square with the square root. So once you get to this point, you can simply just plug in the numbers that we have previously written, and you'll get to this answer. So let's do that. So h plus is equal to the square root of 4.0 over e to the 2 times delta e, which delta e will be e naught minus e, which we can do that calculation. That would be negative, actually that would be positive 0.19. So 0.19 over our 0.0257 volts, and this is volts, so volts cancel. And then when you plug that into your calculator, you'll get that your concentration of protons, of the proton, becomes 1.2 times 10 to the minus 3 molar. So that's another way of using the Nernst equation to solve for a given value. Typically, you'll be asked for the Nernst equation to solve for either the cell potential at a state other than at equilibrium. So you'll be given all the concentrations of the species for Q and are asked to solve for E, or you'll be given E, E naught, N, and some of the concentrations, and you'll be asked to solve for one of the concentrations. So in the former case, that's my video 1. In the latter case, this case is video 2.